All right, everybody, another episode of Tim Rambles On About Wine. This is going to be the second part of our fermentation series. I'll talk about macronutrients, micronutrients, and survival factors. All right, let's talk about nitrogen. Its role in fermentation. The first thing it does is it helps with yeast growth, cell biomass. It also helps with different metabolic functions, so alcoholic fermentation, sugar metabolism, and yeast kinetics. It helps with aroma and flavor compound formation. Different types of amino acids change the way a wine will smell and taste. And then also sulfur metabolism, hydrogen sulfide in that reduction piece. If we don't have enough of these compounds around, nitrogen specifically, we end up with hydrogen sulfide. And we'll talk about that a little bit and how nitrogen plays into that. So one of the things we want to think about is that back to that idea of sugar transport. Well, nitrogen is required for protein synthesis. I mean, enzymes are proteins. So in order for yeast to produce these permease enzymes, they require nitrogen. They have to be reduced all over and over again. Well, if nitrogen runs out, yeast can't eat. That's how they make those permeases to make sure that they can either do the facilitated diffusion or active transport that they so like. And if they can't do that, they can't eat anymore, and you get stuck fermentation. So this is one of those key pieces that we have. We have to be able to make sure that we have adequate amount of nitrogen. So nitrogen's forms. Well, YAN, which we've talked about, is a combination of ammonium, like we get from diammonium phosphate. Some of it occurs naturally, and ammonia, which is amino acids. The thing is that yeast like ammonium a lot. It's like very much easier for them to assimilate. It's not as complex of a nutrient. So that's what they'll use first. And they'll also use it preferentially. So if we're adding DAP, diammonium phosphate, they will use that before they utilize their amino acids. That's important to remember. So that's why we don't always add DAP early on. We wait a little while. And we'll explain that here in a second. So there's 20 different amino acids. Yeast can assimilate all 20, but they don't. They do have a preference for different ones. And so the thing is to remember is the combination of ammonium plus ammonia equals yeast assimilable nitrogen, or YAN. So yeast really likes some amino acids better than others. They're not all the same, but this is a list of the amino acids. Some of them they really quite like, some they really don't. A couple I want to point out on this list, which are cysteine and methionine. These are the sulfur-based amino acids, and they really quite like don't like these. Yeast are not a big fan of methionine and cysteine. They're sulfur-based amino acids, but that's what glue those thiols that give the passion fruit and guava aroma to Sauvignon Blanc. So they're glued to those, and so we kind of have to force yeast to consume them. So if we add DAP too early, DAP actually, diammonium phosphate, shuts down the preference for cysteine and methionine, and they won't go after it. And so you won't get those passion fruit and guava aromas. So it's really important that you kind of pause and wait a minute, because if we add too much ammonium, yeast will shut down the transporter for other amino acids, and they won't use them, and will leave them behind in the wine. So not only will you not get passion fruit and guava, you may leave other things behind in the wine, like histidine or tyrosine. Do you see those over on the list? Histidine and tyrosine. We leave those behind in the wine, and yeast don't consume them, and they leave them behind. Bacteria will come along and chop up things like histidine and tyrosine and turn them into histamine or tyramine, which are very toxic to humans and can cause headaches and heart palpitations and all sorts of other nasty things. So it's pretty interesting how judicious we need to be about use of DAP. So it's why we don't use it right up front. There's a reason we wait for it, because we want yeast to consume as many of these amino acids as possible. And now they don't all like amino acids the same. Some amino acids they don't really ever quite like glycine, they basically never touch. But you can see that you go down to that tyrosine, notice that they don't really like that at all. So it's really important for us to delay that DAP addition as long as possible, because you can see that ammonium is right what they like. Now, not all amino acids are created equally, because arginine is something that they really quite like. You can see that they assimilate it quickly, and there's a reason for that. There's a lot more energy available out of that one amino acid, whereas tyrosine isn't really very good for it. So again, it takes 1 mole of ATP to transport into a cell. So with our, something like tyrosine, they're going to get as much energy out of it as they put into bringing it into their cell. It's kind of a net loss for them. So it isn't the best amino acid. But the fact of the matter is, we need to always do our best to try to get them to deplete these amino acids, which is why we always delay that first DAP addition. So again, taking a look at that amino acid preference by Saccharomyces cerevisiae, some things that they don't consume a whole lot of, like arginine, whereas other things they do end up consuming all of it. But you can see that not all yeast are equal, and you don't always end up with the same amount of amino acids at the end. I think it's just kind of an interesting way of looking at this. Some other stuff that we can't measure outside of nitrogen is we can't easily measure vitamins. So a lot of times we add them prophylactically as a safety measure. So you always ask me why I add thiamine. So thiamine is the coenzyme for producing acetaldehyde dehydrogenase. This is that step between acetaldehyde to alcohol. This is why we add thiamine. It helps yeast ferment completely and reduce the chance of a stuck fermentation. This is what helps them to produce alcohol. We like thiamine. The other reason why we like thiamine is that if we accidentally did leave a little bit behind in the wine, this is what you use as a human to take and create alcohol dehydrogenase, which takes ethanol and turns it into acetaldehyde. You use thiamine. And as a matter of fact, most people that end up dying of liver failure or have a problem with their liver due to excess alcohol consumption, it's almost always due to a nutritional deficiency, not always necessarily due to overconsumption of alcohol. So thiamine is a big role in that. So anytime that, because I do know enough people that work in medicine and things like that, that frequently when they get people in that have been kind of late stage alcoholics, first thing you do is jack them up on thiamine, and thiamine will really help get the liver functioning again. So thiamine is also something, for anybody that consumes alcohol on a regular basis, we should really be looking at supplementing in our diet. The other thing that we add is pantothenic acid. So pantothenic acid is the coenzyme that is the one step before making acetaldehyde. And the reason why we like to add this is that pantothenic acid not only helps regulate fermentation, it shuts down the pathway for producing hydrogen sulfide. So when we add pantothenic acid to the wine, it helps us reduce that potential for having a stinky ferment. So these are the two B vitamins that you see us regularly add. So in addition to having to supplement nitrogen, which we regularly do in Washington, I'm going to talk about, we prophylactically just supplement with a little thiamine and pantothenic acid. Now, if you use things like Fermade or Superfood, some of the proprietary yeast nutrients, they have this blended in. They're already there. I'm just cheap, and so I use DAP and thiamine and pantothenic acid because they're a real bargain way to go, but you can buy much more expensive yeast nutrients. So the question is, what's the right amount of nitrogen? Well, that's a good question. The range is less than 30 milligrams a liter. The lowest I think we've seen is 19. And the highest I've ever heard recorded is 2,400 milligrams a liter, which is insane. According to literature, the minimum to finish ferment is 150 milligrams a liter. And then UC Davis published this chart. At 21 Brix, you need 200 milligrams a liter of nitrogen per liter. 23, you need 250. 25, you need 300. 27, you need 350. Well, the Washington average is about 92 milligrams a liter, according to ETS. So, and the ideal range for the best aroma profile, according to Maurizio Ugliano, one of my old professors at Adelaide, is 320 milligrams a liter. I don't think there's a clear answer here. I think we're always looking for clear answers. I don't think it works. So I'm going to walk you through a few different examples here and talk about what I might do. And of course, I'll welcome discussion later on, but just sort of put you in the mindset of what I'm thinking when I'm looking at nitrogen contents in any particular grape must. So what's the right level of nitrogen? Well, that depends. What do we do here? So we're looking at a Cabernet Sauvignon. We're coming in at a pretty reasonable amount of sugar. Our acid's not terrible, but let's not get belayed by that. Let's take a look at our yeast assimilable nitrogen. It's really low. So what do we do here? This is a pretty simple wine for me to make a decision on. The legal limit of DAP we can add to a wine is 1 gram per liter. That's the legal limit. It's laid out in the TTB Code of Federal CFRs, Code of Federal Regulations. And so when we look at that, all we can add is what is available. And DAP is 22% nitrogen. Repeat that again, DAP is 22% nitrogen. So you add 1 gram per liter, you'll add 220 milligrams a liter of nitrogen. So, bum, 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 if we were to add the legal limit, 220 milligrams a liter, to that 59 that's sitting there, we get 279 milligrams a liter of nitrogen that we can add legally to the wine. So that's about perfect. So with this one, I'm going to go straight to the throat and I'm going to add nitrogen and I'm going to be unabashed about it. Cabernet doesn't really benefit from any funky notes. Hydrogen sulfide is not something we're looking for to enhance our aroma or flavor profile. So this is one we're going to go right for the throat. And we're going to add the legal limit of DAP. And I'm going to split that up between 3 different splits on the fermentation. The reason I'm going to split it up 3 times is yeast or feast or famine. And so if we add it all up front, 1 generation of yeast will get it all, and then subsequent generations won't have any available, and you'll be very likely to get some hydrogen sulfide. So in this particular instance, I would inoculate at, say, 25 bricks. I wouldn't make my first DAP add until around 20, and then I would add another one at 15, and then another one around 10. Obviously, those aren't hard, fast rules, but I would split that up, that DAP addition up into 3 doses, so that that last dose goes in right at that, sort of 8 to 10 degrees Brix range, right before the yeast go into activated transport, and they can still assimilate all of that nitrogen. The other thing we're going to probably do in this in a vitamin sense is we're going to definitely add some pantothenic acid on the front end, and probably move into adding some thiamine midway through the ferment towards the end, in order to make sure that the yeast finish up that fermentation effectively, because this is something that's probably going to end up, even with water back, close to 15% alcohol, and that's a difficult place for yeast to ferment. All right, let's shift gears here a little bit. So this is Rivière-Gallet Mourvèdre, and this is a Rocks District wine. And you can obviously see this was a bit of a late pick and was not something that was on our agenda to do initially. So this was kind of a surprise late one. So this is a wine that's going to require quite a bit of modification. So we did have to add quite a bit of acid. I think we added 3 grams a liter, something ridiculous like that, 2 grams a liter. And then we also watered it back significantly. But take a look at this. We've got plenty of nitrogen, right? There's a lot here. The conundrum with wines that have decent amount of nitrogen on the front end is that sometimes they can get pretty reductive on the back end. So when we made this wine, we had a discussion. We had to think about it. Did we want to really exemplify the roxiness, or did we want to be sure that we had a nice, good, clean ferment? And so after some discussion with the group, we decided the best thing to do was going to be to add a little bit of nitrogen. I don't think we really needed to. If we wanted to really exemplify the roxiness of this, we could have left this alone. And one of the things we see in the Rocks District is, notice that we have really high alpha amino compounds. That's the amino acids. And a lot of times what we see from that region is they're really high in methionine and cysteine. And those can be made not only into some stinky compounds like the thiols for Sauvignon Blanc, they also can make dimethyl sulfide. And dimethyl sulfide smells like canned corn and quince and truffle. And so when I'm looking at this wine going, okay, what do we want to do? Do we want to be terroir expressive, or do we want to kind of get this through ferment? So we decided to go ahead and let it ferment to basically about 10 bricks. And then we did a big DAP add at the end, about half a gram per liter, so about 100 parts per million of nitrogen, about 110 parts, which puts us at about 300 milligrams a liter. So we did a little bit of a late add so that we'd use up all of the natural amino acids, but we wanted to make sure that we had a nice clean ferment out at the end. So we could have probably fermented it as it is and had a little bit more of a funky wine and maybe fought some reduction later on. But that wasn't the direction we went with the group. So we'll have to taste this and see what you think of it. All right, what do we do here? Well, this is Viognier. This is from Lake Olin, and this is a nightmare ferment. This is literally one of the hardest things you could possibly have put across your plate. And why is that? Well, first off, we've got a lot of sugar, we've got low nitrogen, and we've got VNA. So you line all of those up, and this is a picture-perfect stuck ferment waiting to happen. So this is a wine that we're definitely going to be looking at doing a number of things. So first off, we're dealing with VNA. VNA is likely to stick more than any other variety I've ever worked with. So that's step one. Step two, we're also going, okay, we don't have nearly enough nitrogen. And usually when wines are deficient in nitrogen, they may be deficient in other things. So this is a full court press on this wine. We're going to not only bring it in, we're going to press it. We're not only going to plan on that full gram a liter of DAP addition, we're also going to be looking at adding yeast hulls for some hopefully extra, cannibalistic bits and pieces that the yeast can consume themselves by consuming old dead yeast. But this is also a wine that we're going to be very actively adding pantothenic acid and thiamine, not only at the beginning, but also at the end. And then, of course, during inoculation, we're going to want to make sure that we have a very, very healthy yeast cell population going into this. Whenever I'm fermenting Viognier, I don't dilly-dally with yeast strains. We're going to use something pretty aggressive to be able to get through it because it's going to most likely stick. And we stuck it. The good news, even after all that, we still stuck the ferment. But that being said, we did it on skins, and it had horrible smoke taint. And so hopefully we'll let you try it because, wow, it's bad. Nonetheless, if it was a normal vintage, we want to look at this and go, okay, this is a problem wine. We're definitely going to be working hard to get this as a completed ferment. So what do we do here? Now this one, I think, would be a pretty big shock to anybody's system. This is a Tempranillo. Again, we're going back to the Rocks District rather than just cranking up the yeast, the DAP on this one. This is one you've got to scratch your head. What are we going to do here? So this is kind of a contrarian wine because you bring this in, and let's ignore the acid numbers, which are trash, and the pH on it, which is terrible. But if we were to just look at sugar and amino acid numbers, let's go ahead and take a look at that. So we've got pretty decent amount of sugar. This is going to end up, as a red wine at about 14.5% alcohol, which isn't horrendous for a Tempranillo. And if we focused on just the yeast assimilable nitrogen, we're like, wow, look at that, man, 385 milligrams a liter. That is plenty. I don't need to add DAP. And you would be wrong. You would be terribly, tremendously, horribly wrong. So one of the things that's a real conundrum about high nitrogen musts like this is when you've got a ton of nitrogen on the front end, you end up with a really big yeast cell population in the ferment. So right off the bat, they've got plenty of sugar, they got plenty of nitrogen, so you end up with a much higher than normal yeast population. And because of that higher than normal yeast population, you know what we run into? Too much population, not enough food. And you will get stuck ferments. You will get the stinkiest ferments you've ever had in your life. And so what's kind of strange about this is one that we're definitely going to have to add some nitrogen to later on in the ferment in order to balance out that big yeast cell population. So in this particular instance, if I was making a still wine out of this, I would have fermented this probably down to about 10, 12 bricks and then made a couple small adds of nitrogen at the end to guide it on through to make sure that fermentation ended up cleanly and properly. Good news is we didn't ferment it. We fortified it, so I didn't even have to worry about it. But nonetheless, again, when you're talking about nitrogen, it's all about your roles. So this is something I think is going to be best to do in a give and take situation. So I'm going to put this up on the PDF files, and then I want to talk to you guys, you folks, through what we're doing and how we're doing it. And what might be some good decision-making steps for fermentation. But then I get this, and this shatters my core. So we look at this. This is our 2018 Seven Hills Sangiovese. 23 milligram a liter of yeast assimilable nitrogen. What do you do here? Well, we fermented this in amphora. According to literature, this won't finish. Won't happen. It'll get stinky. It'll stick. It'll do all kinds of things. We put it in amphora. We put it in the cellar at about 50 degrees. and it fermented for almost a year. Did it ever get reductive? Nope. Did it ferment dry? Yep. Is it 15.5% alcohol? Sure is. Did it do it without adding any nitrogen? Sure did. So everything that I thought I knew about nitrogen, I don't know. I suppose there are some things that sometimes are mysterious because according to literature, this wouldn't work, but it certainly did. My thoughts is that it fermented so long and slow that the yeast, as they died off, they released their guts back in the wine, and it was basically a 9-month long fermentation that was reliant on cannibalism. So pretty cool stuff, but nonetheless, we'll want to talk about this kind of one-on-one. All right, survival factors. Yeast requirements in the presence of alcohol. What are the things that yeast need in order to finish fermentation? So not only are we thinking about what kind of yeast do we need up front, how are they going to ferment, what is the role of nitrogen in that process, then additionally, what are we going to be able to do to make sure that we have a good solid fermentation at the end? So let's kind of go back to the growth phase, stationary phase, and then decline and death. And the reality is all of this stuff that we need to do to ensure that we have a good death for our yeast really kind of happens here. So ensuring that our yeast start well is going to ensure that they finish well. So let's talk about the things that we need to be able to do that. So during the stationary phase, again, things are basically happening. Basically, during the stationary phase, one of two things are happening. Either yeast cells are dying as equal to the ones dividing and growing, or there's no more division nor cell death. But it's definitely marked by a definite decrease in viable cells. This is where these survival factors come into play. And so why do we want to do it? We want to maintain the viability of yeast cells. We want to increase their ethanol tolerance and maintain their ability to generate energy and finish that ferment. So here's our major survival factors. Number one is oxygen, fatty acids, and sterols. Now, the key thing is that on the front end, during the reinoculation phase and during kind of bringing yeast back to life, yeast use oxygen to make these fatty acids and sterols. They will produce them on their own. So a little bit of oxygen, the citric acid cycle, the respiration products are utilized for amino acid nucleotide biosynthesis instead of energy. So basically, they will make their really strong, robust cell walls. They will also use pyruvate to make fatty acid and biosynthesis. So they will make their own fatty acids. And then glucose, they'll restructure to make their cell wall polysaccharides. So a little bit of oxygen helps them build robust cell membranes. Remember, this is their skin. This is the thing that protects them from what's happening outside the cell. The thicker and stronger their skin is, the more tolerant they'll be to alcohol, and the greater ability that they'll have to regulate sugar, transport into their cell. The other things that we want to add maybe are lipids and sterols. These are involved in structural components of the cell, cholesterol and ergosterol. Oxygen is essential for this biosynthesis. So culture the yeast in the presence of oxygen. All the stuff that you buy, all the pre-cultured yeast, active dry wine yeasts are all cultured in oxygen before they go to sleep. So bring them back. The other thing we can do too is we can add yeast hulls. And these have a lot, so dead yeast have a lot of lipids and sterols in them. So adding dead yeast can be a functional thing to helping those survival factors. This is important to know if you know that you're going into a difficult fermentation environment. You want to make sure you give the yeast every opportunity you have. So a little bit of oxygen, some dead yeast. These are all great things that will help adapt that yeast cell membrane. Without good structures, the cells will leak and die. So what does this mean? Well, a little molecular oxygen will help build a yeast cell wall. This is a well-adapted phospholipid bilayer. This is what a really tough yeast cell wall will look like. So by having enough of these fatty acids around, enough oxygen around, and enough sugar around, and all the right pieces in the right place, we make a really robust cell. and they'll be able to ferment much better. So how does ethanol inhibit yeast? Well, it displaces water, changing the properties of the layer, outside layer of the yeast cell. So it denatures proteins. Remember, enzymes are proteins. So all these enzymes that we're relying on are getting broken down by alcohol. It allows increased passage of acid into the cell membrane. And so as the acid leaks in the cell membrane, the yeast have to balance their inside out. It has to pump that acid out of its cell, and that requires energy. It's really hard for yeast, once we have alcohol, starts breaking down the cell membrane, we're running out of sugar, we're running out of nitrogen because the yeast have consumed it all, and that on top of that, what nitrogen they do have to make enzymes, ethanol is breaking it down. So you can see that yeast are kind of getting hit from every angle on this. So this is basically a kind of cruddy picture, but it looks, it's pretty clear as to what it looks like. So on the left side, we have low alcohol, and you see those two black lines. That's a thick, robust cell membrane. But once we get ethanol in the equation, you can see how that cell membrane starts to break apart. So like if you lace your fingers together, that's like a well-adapted phospholipid bilayer. But as soon as you get ethanol in the equation, it opens up, opens up that cell membrane, and all those amino acids, all the acid that's in the wine leaks in the cell membrane, and then the yeast have to work their butt off, burning ATP the whole time, burning their energy to keep pumping those hydrogen ions out. It's a really difficult place for them to be. And that's the effect of ethanol stress on yeast. So basically, here's the shopping list. Pretty simple. You need oxygen. Oxygen up front. Oxygen is your friend. We need oxygen during rehydration and during active fermentation. It's really hard to oxidize a live ferment. The yeast will use it all. And they will use that oxygen plus pyruvate to make those fatty acids and sterols in order to adapt to ethanol. If no O2 is available, you need to supplement these nutrients. So why this is important is if you're doing a really reductive style Sauv Blanc where you're trying to not oxidize any of those aromas that we like so much. And so when you do these really reductive style of, and I don't mean reductive like stinky reductive, when there's no oxygen around in the grape juice, that's a really tough place to pitch yeast into. And since you can add oxygen because you might oxidize the wine, especially in the juice phase, you're going to have to add something. So whenever we're doing Sauvignon Blanc or these maybe Pinot Gris that we're doing in a reductive style of pressing, you're going to require some extra things. So this is one of those opportunities to add some yeast hulls, add those vitamins and nutrients, and make sure that maybe if you are pitching the yeast, when you pitch the yeast and you're doing that inoculation, you're adding a tremendous amount of oxygen to the inoculum, so that when you pitch them, those yeast are as well adapted as possible, because you can't do it once they're in the juice, or you might nuke a lot of your aromatic compounds. All right, so quick review. Let's talk about nitrogen and its role. It helps produce those permeases to bring sugar into the yeast cell. It also is not just one thing, it's ammonium as well as amino acids. And so all those together make yeast assimilable nitrogen. The other thing we want to remember is our survival factors, which is oxygen. We want to use that in our inoculation stage and whenever we can in a wine in order to help build up that robust phospholipid bilayer so that yeast are more ethanol tolerant. And if we can't do that, we might want to add some other things and add some lipids and sterols in the form of yeast hulls to wines that we may not be able to add so much oxygen to on the front end. And the other question is really, what's the right amount of nitrogen? And the answer is I'm not always sure, because it's not always clear. If you have too much on the front end, you might need to add it later. Sometimes less is nice because then you can tailor in how much you want. And then also consider the types of amino acids and where they come from. And that's not an easy analysis to do. It's something that you kind of learn from vineyard site to vineyard site over the years. So the right amount of nitrogen kind of depends on the variety, but I think it's best open to discussion to figure out what the best solution is going to be in that respect. And that's all. Cheers.